Okay, we're going to go over the problems on the first exam for Math 156. So problem 1 is to find the equation of a line with a certain slope passing through a certain point. So we use the point slope formula for a line from pre-calculus. And our line, I'll just call it line, is going to have slope minus 13 over 22 times x minus 8/5, that's the y coordinate of the point the line passes through, plus 9/4. So that's the line. And if we plot this line, oops, forgot the equal sign. That's the problem. There we are. Line, you assign this to the variable line, colon equals. Now it works out perfectly. And what is the y coordinate? Well, this is already in the form y equals mx plus b. This is the y coordinate, or the y-intercept. So I could say y-intercept, like this, y. It's what we get when we substitute x equals 0 into the line. And it's 703 over 220, just what we would expect. And the x-intercept, well, that's where the line crosses the x-axis. That's the value of x when y, which is this, equals 0. So this is what we get when you solve the equation line equals 0 for x. Or another way to do it is the same thing exactly. It's what we get when we set this equal to 0 and solve for x. And it's the same thing. So that's problem number 1. For problem 2, we want to find all solutions to a certain equation. The equation is 2 times e to something. That means exp is the function. E to the minus x squared over 15. And we want to know when that's equal to 2 plus the sine of x minus 1. So we want to solve this equation for x, and we'll use fsolve because there won't be an explicit solution. So Maple gives us one answer. Now use a graph to check your answer. So let's plot these two curves. Suppose we plot on the same graph this curve and this curve. Now, when I plot it like this, I can see there are two solutions. There are 2 points. So the blue curve is the sine curve. The red curve is this exponential. They cross at 2 places. This only gave me 1 place. So I have to find out where is the second point of intersection for what value of x at least. And I can force Maple to look for x, let's say in this negative range, x going from -3 to 0. Aha. And here we get the second point. Let me use numbers for the measurement on the x-axis. Now, let me say x goes from -3 to 3. And now you can see that this point, -1.75. Let's just look at that point. I want to look at that point a little bit more closely. Yeah, that's right. So this point is just a little bit below 0.9. That's what I wanted to check. Let's just go back. -3 to 3. That's it. This is not the x-axis, by the way, because this is 3, 2, 1. This is well above the x-axis, but you can see the points of intersection. If I include the constant function 0, now you see it properly. That's what it looks like. Okay, that's problem 2. Problem 3 is to compute a certain limit. Let's just write out the problem. The limit of what? The arctangent of 2 times x minus the cosine of 1 over x. And I want all of that divided by something, so I have to put parentheses around it. That's going to be my numerator, divided by 1 plus 5 times exp of minus x. And I want to find the limit as x goes to infinity, and we write, oops, need a comma here, x equal infinity. So with a capital L in limit, that just states the problem. If I write it with a lowercase l on the right, I get the answer, pi over 2 minus 1. Problem 4, we have a certain function, and I want to find the tangent and the normal line to the curve, to the graph of the function at x equal 1. So let me just write this as a function, f of x. So x goes to square root of x to the 4th minus x plus 1. That's my function. And we know the formulas for the tangent and the normal line. Let me just call the tangent line. And that's going to be the derivative of f at the point 1 times x minus 1 plus the value of the function at 1. And the normal line has slope, which is the negative reciprocal of the slope of the tangent line. So let's just see if this works. So that's problem 5, to graph them. So I want to plot together the function tangent line and the normal line. Oops. This is colon, curly brackets. Now it's right. And of course, the blue and the green lines aren't perpendicular the way they're supposed to be. And that's because this is not drawn to scale. So let me do control click, scaling constrained. There we are. Let me just not have it go up so high. So let's say that X still goes from -10 to 10. And that Y also go from, let's say maybe -5 to 15. Perfect. So here you can see the red is the curve, has this little bit funny shape. The green is the tangent at x equal 1, and the blue is the normal line perpendicular to the tangent. Problem 6 is to write a loop to compute the first 7 derivatives of a function. So for n from 1 to 7 do, let me put in my n do. And for each n, the nth derivative, you write, d at n. Now I need a name for the function, so I'll call it f of x also. The only problem is I haven't defined the function, so let me insert that here. So the function for this problem is cosine x e to the x cubed. So f x goes to cosine of x times exp of x cubed. That's my function. And now I've calculated the first 7 derivatives. First derivative is easy. You can do it in your head. It's minus the sine times the exponential plus 3x squared times the cosine times the exponential. But they get progressively more complicated. And by the time we've gotten up to the 7th derivative, you're probably glad you didn't have to do it by hand. Okay. Well, after problem 6 comes problem 7. We have 2 functions. G of x is x to the 6th plus exp of x. And h of x is the function 2 over x. So the composite function, g composed with h of x, is that. Oops. Right. Oops, I forgot to write. There we are. Now we have the function. So g of h of x, you put 2 over x in for x, you get 64 over x to the 6 plus e to the 2 over x. And when you differentiate this, that's what you get. If you want to simplify that, You get the same expression, it only looks nicer. And when you compose the functions in the opposite order, you get different functions. That's h composed with g, and the derivative of h composed with g at x is that. Problem 8 is to calculate some integrals. So the first, we have a degree, a rational function where the numerator has degree 5, the denominator has degree 3. So it's just, let me just write the problem. Integrate. What are we integrating? 2 times x to the 5th minus 107 times x plus 5 divided by x cubed plus x plus 7. And we're integrating with respect to x. Well, that's the problem, not the answer. How do we get the answer? We write down the same expression, but with a lowercase I. Wow. So what this says is we get this polynomial plus something which is too complicated for Maple to do explicitly, which means it can't be done. But there's some number r, which is a root of this equation. And so there's this constant times a log x minus r. That's just what it turns out to be. Can't do anything about it. The second is an integral which looks like an arctangent. We're integrating 1 over 4 plus 49 times x squared. Okay. That's, 4 plus 49. 4 plus, that's right, 4 plus 49 x squared. And to actually compute it, that's the answer. Arctangent 7x over 2 over 14. So those are indefinite integrals. In problem 9, we're calculating some definite integrals. The first is the integral of x cubed times cosine of x, where x goes from 0 to pi. And recall, pi is always spelled with a capital P if it means the area of a circle. All right, that's the statement of the problem. And the answer, we just have to use lowercase I. So it turns out to be minus 3 pi squared plus 12. And for the second, we're integrating 1 over 1 plus 25 times x squared x going from minus 1 2 dots 1. Right? That's the problem. And to get the answer, lowercase I. Two-fifths arctangent of 5. Problem 10 is to write a little maple program to find some prime numbers. Find the primes between 4,000 and 4,300. So we can say for n from 4,000 to 4,300 do. And what is it we have to do? If n is prime, if is prime n, if that's a true statement, then print n. And then just as with do, I have to have an end do. With if, I have to have an end if. So this should be the program. And here they are. These are all the primes in this interval of 3,000, from interval of 300, from 4,000 to 4,300. Those are the primes. Problem 11 is a recursion. We have a sequence where we're given UN, U1, and U2, and if we know two numbers in the sequence, we can find the next by a certain formula. So we have U1, use square brackets instead of a subscript. U1 is equal to 1, and U2 is equal to 2. And then I have to use the loop to compute the rest. For n from, now I have U1 and U2, so I'm going to start with U3. From 3 to 30, do. And I put in my end do always so I don't forget it. So UN is defined to be 3 times UN minus 1 minus 2 times UN minus 2. And what I want at the end is to know what is U30. Okay. So Maple actually printed out all the terms. Oh, this is interesting. If you recognize this sequence, these are the powers of 2. 2, 4, 8, 16, 32, and so forth. And the 30th power of 2 is this. 536,870,912. Problem 12. Compute, first of all, the limit of e to the 1 over n. So the limit of exp of 1 over n as n goes to infinity right? Oops. I stopped. I need to erase that. Clear the memory. Okay. Oops. It should be limit. Yep. That's the problem. And what is that equal to? I need Li. There we are. The limit is 1. Now, just to get some idea of what's going on here, suppose I plot the function exp of 1 over x as x goes from 1 to 100, say. It's decaying. Suppose I plot this together with the constant function 1. So that's this red line at the bottom. Let's just graph this maybe for y going from 0 to 1.2. Yeah. See, that's what's going on. This function is decaying. Now, maybe make it 3. Yeah. So e to the 1 over x, it's decaying and it's approaching 1 in the limit, and it's always bigger than 1. And in fact, it's monotonically decreasing. If you looked at if you differentiated the expression e to the 1 over x with respect to x, you see you get something. The exponential is always positive. X squared is always positive. There's a minus sign in front. This is negative. So that means the derivative is always less than 0. The function is always decreasing, and it's always bigger than 1. So at some point, it's below 1.02. Suppose I actually put in 1.02 in here. So okay. So here's a nice picture of what's going on. The green is my function. As x goes to infinity, it's decaying, it's approaching 1, and it's always bigger than 1. And this is the line 1.02. And at some point, it's below 1.02. And I want to find this point. So find the smallest positive integer n such that e to the 1 over n is less than 1.02. So for what integer n is the green curve below the blue line? That's what we have to figure out. And there are a couple of ways to do it. One way, once you have this graph, is to blow this up in this region. So Command C, Command V. Let's plot this maybe between 50 and 60. Uh-huh. I'm just magnifying this. Uh-huh. So there's some point right around here where the green crosses the blue line. So maybe I'll go from 48 to 52. Uh-huh. It's hard to see, but somewhere here, see, what do we want to find? The smallest positive integer n, the first integer for which this falls below the line. So maybe I'll graph this from, let's say, 49.5 to 50.5. Oh, hard to see what's going on. So okay, so here you can see the green is the curve. It's above 1.02, and then right here, now it's below 1.02. So when x is 50, the curve, the value of the function is bigger than 1.02. But when you get to 51, it's below. So the answer is 51. 51 is the first integer where e to the 1 over n is less than 1.02. Now, there's also another way to do this, writing a program. So that's maybe we'll guess that the number is going to be between 1 and 100. So let's say for n from 1 to 100 do, put in my n do, and let's put it like this. If exp of 1 over n is less than 1.02, then print out the n. And if. So I'm going to look at all the numbers from 1 to 100, and the first time, and whenever e to the 1 over n is less than 1.02, I'm going to print n. So the first n that's get printed, that's going to be the answer. So let's see if it turns out to be 51. Why is that not true? Let me write this as like 1.0. Let's make everything a decimal. Ah, fantastic. So starting with 51, e to the 1 over n is less than 1.02. I had to make this a decimal, so this will come out as a decimal. I just replaced the 1 by 1.0, and I get 51. And there are other ways to do this, to write this program. So you just get the answer and stop. So let's see if we can figure out a way to do that. Let's introduce a sort of a dummy variable, I'll call it k. And let's say that k equals 0 to start. And then I'm going to write my program. It's almost going to be the same thing. And I might have stored a value for n, so let me just come up here and clear everything in the memory. So if, let's write it like this. If k equals 0 and this is less than 1.02, then I want to do two things. I want to print n, and I want to let k equal 1. And now you have to think a little bit about what this says and why and how. So I start off telling k to be 0, setting k to be 0. And then I look at the first 100 numbers. And for each number, if k is 0, and this is less than 1.02, the first time that happens, I print n. But also the first time that happens, I change k equal to 1. So when we go to the next number, k is not equal to 0, so nothing else will be printed out. So it should be, I just get the answer immediately and nothing else. Yep, 51, that's the answer. Anyway, it's nice thinking about this program, and there are also other ways to write a program that does this. Okay, so that is the solutions to the first exam. So let me stop the recording.